Page 633, lesson 10.4 is on solving radical equations. Radical equations, what that means is we have an equation, something with an equal sign, and then also somewhere in the equation there's something with a radical, something with, most likely for you guys' case at this point, square roots. So basically the gist of this, if you read through this paragraph here, those two sentences, that's kind of the gist of what we need to do. So just to make sure for people that are watching this video later that they can see this, let me just get that up a little bit bigger on the screen. So these are the steps that we're going to need to do on these problems. First thing is we're going to need to isolate the radical. We need to get the radical by itself if it's not already by itself. And then after we do that, we need to square both sides of the equation. And then we'll have to probably do some other stuff, maybe add or subtract, maybe something else besides that. And then we'll be able to get the variable by itself. Sometimes we may have variables on both sides of the equation, so we may have to do some of our other steps that we've done before with solving equations. But isolating the radical and squaring both sides, that's the first two key steps when we're doing these problems. Okay, so if you look at problem 1, they're wanting us to solve this equation. So to solve this equation, first thing would be isolating the radical. So you could subtract 7 on both sides, and then they squared both sides, and they got x equals 81. At that point, they just substituted that back in the original equation to make sure it works. So square root of 81 is 9, and then 9 plus 7, 16, so then that works. So for the got it 1, trying to work this out. First thing, isolating the radical, we can add 5 on both sides, which would be 3. Then the last step here for this problem would be square both sides. So x equals 9. At that point, that's a real quick check. If you have like 10 seconds, you could substitute that back in the equation and just verify that it does work. And it does, so we know we got the right answer. So if you look at problem 2, this is just an application, just a question that involves a formula that has a radical equation in it. So I'm not sure who figured this out, but apparently the time it takes for a pendulum of a clock to complete a full swing can be approximated by this equation. Somebody must have had a lot of time on their hands. So in this equation, L is the length of the pendulum in feet. And so if the pendulum of the clock completes a full swing in 3 seconds, what is the length of the pendulum? Round to the nearest tenth. So T is the time it takes for a full swing. So they put a 3 in place of T. And then we're trying to figure out what the length of the pendulum is. One thing different, well, not different than what the directions were that we said, but different than the last problem we did, is that we need to divide by 2 on both sides to get the radical by itself. On that last problem, we had to add to get the radical by itself. So, just different methods there that you might have to look at. So divide by 2, and then they squared both sides. And then at that point, the variable is actually not by itself yet. It's still being divided by 3.3. So you could multiply by 3.3 on both sides, and then you get the answer. They said on this one, I think, to round to the nearest tenth of a foot. So they did go ahead down here later after they checked their answer. They rounded it off and said it would be about 7.4 feet long. So if we look at the got it, how long is the pendulum if each swing takes 1 second? Again, we'll just start with the formula that they gave us. So here's our formula. The time is 1 second, and then we're trying to solve for L. So the steps are the same as what the book did, so we won't take too much time with this. The first thing, just like the book did, you can divide by 2. Since we already have a decimal on the right side, and since 1 divided by 2 comes out evenly, I'm going to go ahead and just put that as 0.5 instead of putting it as a fraction. So next we need to square both sides. So that would be 0.25 equals L over 3.3. So then next, the variable's being divided, so we need to multiply by 3 3/10 on both sides. And that comes out as 0.825 feet. On the previous example, it said round to the nearest tenth. Technically, this problem did not say anything about rounding, so if you just kept it like that, would be okay. If we assume that we had the same directions, it would have been 8/10 of a foot would be the length of the pendulum. If you look at problem 3, the difference here is that we have radicals on both sides of the equation. And that's okay because they're both isolated. They're both isolated just on separate sides of the equation. So what we need to do here, we just square both sides. Once you square both sides, then we're back to things that we've done before. So trying to get the variable on one side, they subtracted t on both sides here, or subtracted 1t, and then they added 11, and then they divided by 4. So they got t equals 4. Then they went ahead and substituted that back in the original equation, and it worked. So they got the right answer. So let's look at the got it 3. So this problem, the radicals are isolated already. So we can go ahead and square both sides. So it's up to you how you want to do this next part. I'm going to go ahead and work with the variables. I'm going to get rid of the one with the smaller coefficient. So if you subtract 5x on both sides, and then that gets you to a two-step equation. And just to finish out here, then we could add 4 on both sides and divide by 2. And then we get x equals 7. At that point, you'd want to go ahead and substitute that back in and work it out. Left side, you'd have under the radical 49 minus 4, which would be square root of 45. On the right side, you'd have under the radical 35 plus 10, which would be square root of 45. So that works. So that's the correct answer for that problem. So the next part talks about if we're solving equations where we have to square both sides, we're creating new equations. And that new equation could have solutions that actually don't work. So for example, if we have to start with x equals 3, if we square both sides, now we've got x squared equals 9. So if you have x squared equals 9, if you think about what could the value of x be, you could say, well, 3 times 3 is 9, so 3 would work. What about negative 3? Negative 3 times negative 3 also is 9. So it looks like that would work, but actually we started out with already the answer. There'd really be no reason to square this because we already have the answer. But we started with x equals 3, and then you see as we worked through that, we got then that x could either be 3 or negative 3. So we introduced a solution that actually is not a solution. And that's called an extraneous solution. The first part of extraneous is extra. So it's like an extra solution. It's a solution that doesn't work, basically. So that's why it's good to substitute numbers in. If you look at problem 4, there's an example with this extraneous solution. And basically, it's always good to check your answers if you have time, but basically, the problems where we don't have a variable that's squared, and then by squaring both sides we get a variable that's squared, that's where we're going to get an extraneous solution. So if you look on problem 4, on the left side we just have an n. When you square both sides, now we have an n squared. So with just an n, I'm thinking I should have one solution, one possible solution. Now I've got n squared, now I've got 2 possible solutions. So I've just introduced an extraneous solution into this problem. But that's what we need to do to solve it. Then we just got to figure out which one's the actual and which one's the imposter, which one's not actually the solution here. So square both sides, and then they subtracted n and subtracted 12, and then that was actually factorable. It factors as n minus 4, n plus 3. If you guys wanted to, if you have problems with the factoring, you could do quadratic formula if you wanted to, but if you're, you guys should be good enough with the factoring that you can probably get that figured out quicker this way. And then when you solve, it says n equals 4 or n equals negative 3. So if you substitute those back in the original problem, if you put a 4 in, that works. If you put a negative 3 in, that does not work. So negative 3 is an extraneous solution. So actually the only solution is n equals 4. So let's look at the got it 4. So for this problem, we'd want to go ahead and square both sides first. Over here on the left side, be careful with this. Negative y is what we're squaring. Negative y in parentheses, negative y times negative y. That would be a positive y squared. And then on the right side would be y plus 6. Notice we have a squared term and a y term. So like we were talking about previously in the book, we're going to need to go ahead and set this equal to 0. If you want to do that all in the same step, you can. If you want to take 2 steps to get there, that's fine too. And then they're usually going to be pretty nice to you guys on these, I think. I would try to factor, and if it doesn't factor, you can complete the square, use quadratic formula, but I think for the most of these problems, they're going to be nice and make it factorable. So this one is factorable. We try and factor this, and it's going to go y plus 2, y minus 3. And then we can set each of those factors equal to 0 and solve. So it's going to say either y equals negative 2 or y equals 3. Now, like I said, one of these is not going to be an answer that works. So if you go back to the original equation, if you try a negative 2 first, opposite of negative 2 would be a positive 2. Is that equal to square root of 4? And it is, so that works. What that should mean, since we created this y squared that wasn't there before, it should mean that this other one doesn't work. And we can see negative 3 is not equal to the square root of 9. That should be a positive 3, not negative 3, so that doesn't work. So what you can do then is just cross out the y equals 3, and then we can just circle y equals negative 2 as our answer. Problem 5, if you look at this equation, just like we've been doing, they isolated the radical first, so they subtracted 8 on both sides here. So they got square root of 3y equals negative 6, and then they squared both sides. They got 3y equals 36, and then they divided by 3. They got y equals 12. So y equals 12, if you substitute that back in the original equation and work it out, on one side you get 14, on the other side you get 2. 14 is not equal to 2, so that actually doesn't work. And that was our only solution. So what that means is our only possible solution was extraneous, and so that means we have actually no solution for this equation. There's no value of y that can make this work. So if you look at the got at 5, we've got a problem we can look at here. So we're trying to get the radical by itself first here. Notice this is a positive 6. So to get rid of that, we need to subtract 6 on both sides. When you do that, make sure you bring down this as a negative square root of 2x. And then we technically don't have our radical quite isolated all the way, so we would want to divide by negative 1 on both sides. And then you can square both sides. So that would be 2x equals 16, and then divide by 2 would be x equals 8. Like I said, always we want to go back to that original problem and make sure it works. So once we get x equals 8, let's try that out and see what happens here. So the question is 6 minus 4 equal 10, and the answer is no. So that actually is an extraneous solution. We have no solution for this problem. So the question might be, as you go through these problems, how do I know if it's going to end up being a no solution? Is there a way that I can tell whether it's going to be a no solution? So actually there's a way to tell sometimes without working through the problem all the way whether it's going to work or not. So on this problem, the radical is already isolated, and so I can actually tell that this is not going to have any solutions because what they have is the square root of something equaling a negative. So, I mean, it has no real solutions, we should say, I guess. You guys will talk about in high school about the imaginary numbers, but that's the reason. You can't have, for our purposes with real numbers, the square root of something can't be equal to a negative number. So if you notice when we get to that point, like on that last problem we did, once we divided by negative 1, we had square root of 2x equals negative 4. If I would notice it at that point, I could technically say there's no solution. Realistically, it's not really that many more steps. If you don't notice it, it's not that big of a deal. Just to finish working it out and then try it and see that it doesn't work.